A slight change now. We're moving on to the Lloyd's Register Foundation student competition. So over the course of the next hour and a quarter, before we go to the break, we'll be looking at the competition. We'll be seeing 9 students come on stage to present their material. And very much this is the live competition, and then the award and the prize will be announced at a dinner this evening. So I will now hand over to the competition chair, Professor Michael Fitzpatrick, who will give you a lot more information.
Thank you very much. Afternoon, everybody. So just to liven things up before the tea break. I felt a bit like the court jester with this. Richard said I wasn't going to be the comic relief, but then he gave me this. And I want this to evoke a reaction in you. If you hear this, I want you to burst into a round of applause. Thank you. Right. So we have 2 parts of the programme, which is an opportunity for some of the students who are funded by the foundation to present their work. Where we had lunch, you'll see that there are posters around the room. These are prepared by the students, summarising what they're working on. Do have a look at them. There is a competition for the posters, so they are going to be judged, and the winner will be announced later. But for now, we have a short talk presentation. And every year we do this a bit differently. This year we're challenging the students to talk to us without any visual aids. So the presentations will be short. They will be 3 minutes. No visual aids. We have a panel of talented, skilled, and entirely incorruptible judges who will then score these students on the clarity of their presentation, its technical content, how good they are at responding to questions. There will be 2 minutes to respond to questions. I will be timing the students. What I'll do is I'll have the timer on my iPad. I'll give a wave when there is 1 minute left. I'll stand up and come to the edge when there is 30 seconds left. And if it counts down to 0, I will go, and you will break into applause. Perfect. So the students, we've lost one, unfortunately. Robert Lee is unwell and can't be with us. We're going to go through in alphabetical order. So to start off, I would like Alexey Berdyugin from the University of Manchester to come and take the stage, please. Great. Okay. So do you have the microphone?
Hello, hello. Can you hear me?
Okay. So I will give you 3 minutes, starting.
Hello, my name is Alexey. I'm Lloyd's Register Foundation doctoral student, and I'm doing my PhD under the supervision of Andrei Gaim and Irina Grigorieva, known for the graphene discovery. I'm really pleased to be here to tell you about our recent work on magnetohydrodynamic in graphene. Our main goal of study, our main focus of study was on a second, or also called Hall viscosity. This is a physical quantity which has never been observed before. Now, let me tell a bit more about this property. It was attracting the interest of scientific community over decades. It was broadly discussed in theoretical literature on fluid mechanics, plasma physics, condensed matter physics, and so on. But yes, any experimental evidence of it was lacking. There are several reasons for it. First of all, in comparison with ordinary viscosity, it cannot be revealed in a standard friction experiments, because this viscosity is dissipationless. So that's the reason for it. And there is other reason why it wasn't observed before. To observe this subtle transport property, one needs to break down the time reversal symmetry. And this property usually cannot be broken in ordinary liquids. But we can circumnavigate this problem to electron liquid, where we can break down the time reversal symmetry by applying the magnetic field. And recently it was found that in graphene, electrons exhibit a fluid-like behavior. They behave as a very viscous fluid with viscosity 100 times larger than the viscosity of honey. But there is an obvious difference between honey and electrons. Electrons have a charge, and if we compare their behavior in a magnetic field, it will be crucial. While honey just doesn't see any magnetic field, we found that electron liquid reacts on it in a very unexpected way. we found that it creates the electric field opposite to the ordinary Hall effect, which is the basis of condensed matter physics in our days. This branch of classical behavior is a smoking gun of the Hall viscosity. And analyzing this breakdown, we for the first time was able to extract the values of the Hall viscosity from the experiment. Furthermore, we showed that in a magnetic field, ordinary viscosity of electron fluid tends to disappear. And our work opens the door to study magnetohydrodynamic. And graphene devices can be used as a simulators to modulate the astrophysical systems governed with the same magnetohydrodynamics laws. Thank you.
Excellent. So we have 2 minutes for questions. So questions, please.
Yes, please.
Tim.
Thank you. Really interesting, really fascinating. How do you explain to your mum what you do?
I explained that we found a unicorn.
So, I have a question.
Yes,
I was at an event recently where with somebody from he was actually from the London shipping industry. He has the company that runs the water buses, and he had obviously misunderstood the potential of graphene, because his question was, when are we going to have the first graphene boats? So when are we going to have the first graphene boats?
Whenever we will make it.
Fair enough. Any more? Okay. In which case, thank you very much.
Thank you a lot.
Thanks. Our second student is Elizaveta Gedris from the Admiral Makarov Institute. So, Elizaveta, would you like to come and take the stage, please? No. Not here? No, concerned looks. Okay, right, moving on then. Bad luck, Muntasir Hashim from the University of Manchester is going to have to come up 3 minutes earlier than planned. I'll be sitting there and I'll give you a wave at 1 minute, okay? You have to use the handheld one, I'm afraid. Afraid not, we've run out.
Hello?
Okay.
Is that okay?
That's perfect. And your 3 minutes starts now.
A metallurgist from Sheffield was studying erosion when by chance he made a steel resistant to corrosion. The key to it was chromium, which formed an oxide layer, invisible protection that could even self-repair. In time, the local factories would make it by the ton and proudly mark the city's name on goods for everyone. It has so many uses, from fastenings to tools, architecture, transport, and the processing of fuels. So, ladies and gentlemen, please raise your forks and knives to celebrate a man whose work has so enriched our lives. Shout it from the rooftop, let the church bells peal. 3 cheers for Harry Burley, who gave us stainless steel. That was Man of Steel by Higgs. So from the poem, we gathered that stainless steel has chromium, which forms a protective layer by combining with oxygen, making it resistant to corrosion. Now, when and where this protective layer breaks, corrosion starts to take place. Localized corrosion starts to take place, resulting in corrosion pits. Corrosion pits are dangerous, and they compromise structural integrity by being stress concentrators and initiating cracks. They initiate cracks. There's been a lot of research on the mechanisms of pitting corrosion. And if you give a crack to a structural integrity engineer, they can calculate the crack growth rate and tell you the remaining life of the component. However, the pit to crack stage is not well understood, and my research contributes to this aspect of the lifetime assessment of a material. I'm using stainless steel and a specific grade called 316L. And what I'm doing is I'm carrying out fatigue tests. So what we call is, at a given stress, I run cyclic tests and I monitor the number of cycles to failure. Then I add a salt environment to it and then again monitor the number of cycles to failure. And obviously, the number of cycles to failure reduces. And then when I introduce single corrosion pits on these specimens, I get a further reduction in the fatigue life of the system, of the material. And, but with this, I have found the knockdown factor of the corrosion pit. Hence, with my research, we've gained invaluable insight into the pit to crack transition. And with this, we can monitor, with this, we can better assess lifetime of a material. Thank you very much.
Questions, please. Okay, well, I have one. So, how common? Sorry, that's not the right word. How is it possible to extrapolate? If you see a pit of a certain geometry, can you accurately predict the life that it's going to give, or the life reduction that it's going to give?
Well, this is what we are studying at the moment. So this is what I'm studying at the moment. So you will obviously need a few more parameters to feed into the work. So what I'm doing is I'm designing experiments so to simulate that kind of environment. So as I've mentioned, so I make single corrosion pits at very specific location and then run fatigue tests to see how it differs from the reference data that is in air with no faults and no, what do you say, compared to an ideal environment. So how does the pit impacts the fatigue life, let's say, performance of the material.
Thanks. Tim. Oh, sorry.
Alexey, Chief Scientist and resident of Sheffield. Can you explain to us how the work that you're doing will make steel a safer material for use in industry?
So basically, stainless steel are prone to pitting corrosion, and because they're used in marine environment where you have a lot of salt. So obviously you get pitting, now what we are not able to assess is when will a pit start to crack. And this is a very important stage for lifetime assessment of the material. Because like I said, a structural integrity engineer can see a crack and calculate the crack growth rate and tell you the remaining life of the system with good prediction, with reasonable confidence. But when you have a pit, right now the current approach is, I believe, they have a standard where they see a certain area of pit and then they either keep it or not. So in this case, the material is not conserved probably, and it could be safe, it could not be safe. So there are these questions that the pit to crack transition, this transition stage of when a pit transits to a crack will solve.
Okay. I think that gives us now 2 minutes. Thank you very much indeed. Thank you. Our next presenter is also from the University of Nottingham, so I'd like to invite Susie Naybour to come up. Okay, so I'll start waving at about a minute, okay? No, there you go. So Susie, I'm going to put 3 minutes on the clock. And you're off.
Hello everybody, my name's Susie, I'm from the University of Nottingham. Could you just give me a wave if you got on the tube to get to this conference today? Okay, and I guess the rest of you could afford taxis, or something like that in London. So you wouldn't be alone today and getting the tube. There's about 5 million other people who are also going to make that journey just today. But all you really hear is people complaining. They say it's noisy, it's hot, it's smelly, it's expensive, it's always late. But is it safe? If you ever stop to think that you're travelling on a network, some of which was put in place 155 years ago, And it's mixed up of this hodgepodge of old, quite old, very old, and then occasionally a little bit of new bit and some new bits in there too. And it actually works incredibly well together. It's so rare nowadays that you hear of accidents such as the King's Cross fire or the Moorgate disaster that result in a mass loss of lives. And the risk management processes put in place following the King's Cross fire completely revolutionised the way that Transport for London approached risk management on an underground railway. But this is where my project comes in. 30 years after that, when we have more data, more powerful computers than ever before, can we do it faster, more informative and more powerful than we have been doing? So in my project, I've done 2 applications in 2 key risk areas, one looking at switch and crossing failure and the derailments that can occur there, and one looking at fire protection systems on underground stations. I've applied a PetriNet methodology, which basically allows you to consider all different component states and various different methods that components within these systems can fail. This methodology allows you to include loads of different maintenance strategies, inspection strategies, and to test how these are going to impact the overall risk of failure on these systems. These models can also be have additional data added into and used to make predictions in the future, and you can optimize them to get the best solution. But they're very slow, computationally very slow, especially with optimization. So the final bit of my project, I've borrowed a machine learning tool and I've made these models smaller. And basically the small model learns from the big model the best parameters that it can use to recreate the results that you can generate from a big model in a much smaller, computationally quick option. Basically, this means if you want to find your optimal solutions, like when should you optimize, when should you do maintenance, when should you inspect, you have a small, compact model that you can do this with. So in summary, I've been doing a bit of modelling on a few systems. They were really slow. I've made them faster, borrowed some bits from some other areas. And I came to this conference in my first year and someone said to me, does it work? I said, ask me in my third year, and I can confirm that it does. Thankfully.
Perfect. Right. Questions, please. Thanks.
I'm just a member here. A couple of years ago, we had steam engine run for the first time in about 100 years ago. So here's the question. A couple of years ago, they ran steam trains to celebrate the anniversary. Would your risk modelling be able to cope with a steam train going through the tunnels, possibly cleaning them for the first time in 100 years?
I mean, I would probably highly recommend that you didn't, because there's a whole lot of toxic smoke, and a tunnel is definitely a very vast ventilation hazard. But I mean, on a serious note, the models are very flexible, and if you want to apply this methodology, you can pretty much apply it to any sort of risk modelling. You just need a bit of knowledge from the person who's producing the model. So, in theory, yes, but I wouldn't want to personally.
Thank you. Richard.
Great talk. Your methodology feeds into better operation maintenance. Can it feed into better design?
Yes, so it has been applied in other papers as well. So you can specify different design options and then run your simulations to get some answers for that. And then you can also link them together through a different, something called a Bayesian network, but you probably don't want to know about that too. But that can help you choose the best option as well. So yeah, it's very flexible.
Okay, great. Oh, one more. Go on, Mark.
Mark Essie from the University of Western Australia. So how do you know it's working? How did you verify your model?
So I've done a bit with some sensitivity analysis. So when you put different values in, do you get sensible values out? It's fairly, the modelling approach is actually very straightforward. It's quite intuitive, you could say. So you just put your different states in. When you do it, you kind of make a net. The bigger you make it, the more complicated, the smaller you make it, the more assumptions. So yeah, for the data and the results I've got, it all seems to tie in nicely. So yeah.
Okay. Do we have one more? No? No? Okay, we're done. Oh, Tim has one. Tim hasn't. Go on. Since he's one of the judges, we better let him have his way.
I think it was really interesting as well, just sort of picking up on Richard's question. Are there any limits to the sorts of things you could include within your model? I'm thinking of some other work that sort of looks at the the tube system these days and how it's getting hotter and hotter because of all the heat that is trapped within the rocks of London. So can you incorporate those sorts of things into your model in a sort of design for a better tube system?
Yes, so say you had, the problem is if you're using the modelling approach that we currently have, this Petronet approach, the more you model, the bigger it gets, and the slower it is, and the more computational effort, you need a supercomputer, all sorts of things. So if you wanted to build a model just for how the tube system's going to change with a few small considerations as it gets hotter, that's very possible. If you want to build something that's massive, considers every asset on the tube and how the temperature is going to affect that, you're going to struggle with your computational effort at the moment, which is really why I've done the little bit on how you can shrink it down, but that's very in its initial stages. So yeah, in summary, in the future, I hope it could do everything, yes.
Okay, thank you very much, Susie. Great. The next talk will be given by Roman Repin from Aalto University. So, Roman, if you could come up. Okay, so I will give you your 3 minutes, starting now.
Hello, I'm Raman. I'm working in marine technology, more specifically in the field of ice engineering. So if you like, you can call me Iceman. And literally, ice is the biggest obstacle for the vessel to travel from point A to B. But you might ask, like, why would we like to travel in the frozen sea? Well, there are reasons. Obviously, we want to tap into huge oil and gas reserves in the Arctic, as well as we would like to make use of shorter shipping route across the Arctic Ocean. So you see, if you want to get honey, you know how to tackle bees. And to tackle these issues, people throughout history have come up with some engineering solutions like vessels capable of breaking the ice. And in order to design those vessels and estimate their capacities, empirical methods were and are still quite largely used. And these methods work fine as long as your vessel and conditions in question are similar to those included in the empirical database. But imagine if you have something like outside this. What would you do? You would need to come up with some other solution. And this is where my work starts. So I follow a different theoretically sound path to analyze ship-ice interaction. To do that, I do a deep fundamental research into how ice fails and behaves when contacted by the vessel. But firstly, I need to characterize it as a material. I need to characterize its behavior as a material. And here it comes to my mind that some people say that they're as smooth as ice. Probably you hear that. But is ice itself as smooth as ice? And to sort it out, let us focus on what I'm working on right now. So if you imagine a block of ice and a piece of steel together, and probably you would think like they are both coherent materials. But in fact, ice is not. Yes, ice, compared to steel, it would also contain of some individual crystals, so-called grains. But the point is that connection between those grains would be much less rigid compared to steel. And these local weak spots lead to the fact that deformations in ice become dependent upon the grain size and the speed of the loading. And in my current understanding, this leads to huge effect on the scale of overall ship-ice interaction. They should be taken care of properly. And to do that, we carry out direct laboratory tests in a fully controlled environment where we gain some knowledge and we apply that knowledge in our numerical methods, and results obtained from those methods that are later validated against full-scale observations. So I hope I've familiarized you with some key points of my research, and now you know that ice research is a hot topic. Thank you.
Brilliant. So questions, please. So I have one. So if you're looking at ice as being a hazard, to what extent does assessing it differ from running into a rock?
Well, in some terms, it's quite similar, I would say, because it's a mineral, and well, as a material behavior is quite similar. But the point is that, as I said, literally, there's no humor in that. Ice is a quite hot material. Do you know why? Because we use it at a temperature close to melting point. That's why we see there a lot of different phenomena, for example, that we would see somewhere in steels that would work in gas turbines, for example. So to some extent it's similar, to some extent it's very different.
Thank you.
If I answer your question.
Anyone else? Yes, Mark.
Yeah, as I said, I'm from Australia, so I know a lot about ice. More about, you can call me Sandman, but on to my question. If you could solve sort of one thing to make life and property safer at sea, as it's interacting with ice, what would it be? What's the big sort of grand challenge to solve in maritime space with ice?
Well, how would it make it safer? Well, let's see. In my current understanding, like typical ship design, optimized for open water, for bigger efficiency in terms of transportation speed and those things, it's not really well equipped for ice-infested waters. And if we just go a little bit further into that, if we equip it better, it will be safer in terms of fewer cases of accidents, lower probability of damage and those things. So, well, it's still the matter of research, I would say. So, but let's see. I hope it will lead to something safer.
Okay. Thank you very much. Our next two talks are from the ICON Research Network, the International Consortium of Nanotechnology. So I'd like Adel Samsudin to come up, please. So I'll give you a wave at a minute. Stand up, okay? So 3 minutes, when you're ready.
Hi. You guys know hydrogen, right? Hydrogen gas is one of the most promising energy source. One of the cleanest and most promising energy source that we can find. It is also useful there's potential in applications or energy-based applications in automotive and power generation. Because it is highly energy dense, renewable, and in a way it's eco-friendly in nature. But using hydrogen gas is not exactly safe. It raises some safety concerns because it is highly flammable and explosive when it is in concentrations with air more than about 4%. Systems that utilize hydrogen gas, they need to monitor it safely, accurately, and constantly monitor any leaks that happen. So sensors in such that detects such leaks need to be fast, accurate, highly reliable, miniaturized, has a fast response and recovery time, and uses low power for operation. Hence, sensors that are available in the market right now are usually using metal oxide films, such as zinc oxide, stanno oxide, titanium dioxide, and these are the sensing elements. So these sensing elements require high temperature to operate at about 400 degrees C. So this requires a lot of energy over a long period of time to be used. So what I can tell you is that using nanotechnology, we can solve this issue by using 3D graphene. 3D graphene is a highly porous network of graphene which can accommodate many palladium nanoparticles that will react to hydrogen and detect hydrogen. So this arrangement does not require heating. It is quite low energy, and it can be miniaturized and detects, and it satisfies all the conditions. So I So this is the work that we are doing, and they are quite promising indications that it's going to be better than metal oxide film. Thank you.
Okay. And questions, please.
Questions for the floor?
Well, one at the front.
Thanks. I'm Kieran Shah from the National Space Academy. My question is about how you have been creating your graphene proto-sensors. So what kind of manufacturing process are you looking at to make these?
We use a CVD system where we degrade ammonia gas to form on a nickel film for the porous 3D graphene. And remove the nickel, and then we secure it with polymethyl acrylate so that it's selective and it's more stable. You know, in short. You're welcome.
Okay. Tim.
Most of us, I think, are more used to considering graphene as a 2D material, which was the big breakthrough. You're talking about using 3D models of graphene. Can you give us some indication as to how big your sensors are? When you've manufactured them and you're experimenting with them, how big are they?
It could, how big it is limited to the size of your tube. So you can get like big, you can purchase like a big foam of copper or a big foam of copper, and then you can just put it in the tube, and from there you can go, and if your tube is 1 meter long, then you can get a 1 meter long size 3D graphene and limited to diameter of your tube. Nickel foam, yeah.
Okay, so ultimately, if your research is as successful as you want it to be, then this 3D graphene structure will be used as a sensor.
Yeah,
how big will the sensor be?
How big? We can cut it to small pieces, right? Maybe about 5 millimeters to 5 millimeters. And we attach electrodes and measure the response to hydrogen gas. Yeah, of course, definitely we have to decorate it with palladium so that it's sensitive to hydrogen. That you can do palladium or you can do platinum, but palladium is cheaper than platinum. Yeah.
Okay. Oh, one more.
Thank you for your talk. What do you think the challenges are to scaling up this technology into more commercial production?
Challenges would be, I guess, the optimizing the based on the geometry of your equipment of the furnace. Otherwise, I don't see much problem in scaling up. You could grow it. It can grow in less than about. It can be done. The deposition can be done in about 3-4 hours per batch. To get a pristine graphene will be around a day. So I think it could be optimized more, and I would say it's ready for. In that way, there's not much challenge in going for mass production.
Okay, thank you very much. Well done. Okay, next we have Theresa Schoetz, also from the International Consortium of Nanotechnology. So the floor is yours. 3 minutes when you're ready.
Wouldn't it be awesome to do all of our daily driving quietly while keeping our air clean? So this is becoming reality for people who are driving electric cars with batteries. Electric cars can reach up to 200 miles today. This is especially possible due to high-performance batteries such as lithium-ion. But there's exactly the devil in the detail. Burning lithium battery packs, difficult recycling, and limited raw material resources of lithium raise severe issues against its safety and also future sustainability. For these reasons, I used to think electromobility is dry, tedious, and difficult to realize. But let me tell you, the day we are all going to drive electric cars is coming. Why? The truth is, fossil fuels are running out in the near future. So let's talk future and imagine an energy storage system which shows high performance, sustainability, and safety. There's actually a strong movement in the battery community towards alternative sustainable energy storage systems. I wanted to be part of this movement and dedicated my PhD to the development of an alternative battery system based on aluminium, conductive polymers, and ionic liquids. Well, aluminium is absolutely sustainable as it's highly abundant and easy to recycle. But the focus on my work lies on conductive polymers. Conductive polymers are unique. They are acting as battery and capacitor material at the same time. They are able to reach high specific power and energy, exactly the characteristics which are needed for electromobility. High power to speed up and high energy to drive long distances. The proof of concept study of our battery system showed very promising results and were already in the range of commercial batteries. Great. Yeah, well, you know, it's almost too good to be true. Unfortunately, our battery died after already a couple of charge and discharge cycles because the polymer was unstable. Within the last year, I put all my effort in the synthesis of stable and well-performing conductive polymers by studying the interaction of the polymer with the ionic liquid. I'm keen to tell you that we managed to synthesize polymers which were stable over 1,000 charge and discharge cycles, and also showed new insights as battery material. But to tell the whole battery story, in the next step, I'm going to test these cells with the new polymers and try to top our initial performances and get in line with state-of-the-art high-performances batteries. Like Nelson Mandela used to say, it always seems impossible until it's done. Thank you.
Perfect, thank you. And questions? Well, I'll ask one. So, will the system offer improvements in safety over the conventional technology?
So, conventional technology means at the moment lithium-ion batteries. Yeah. And the problem there is, for example, the flammable electrolyte. So in our systems, we are working with ionic liquids and they're non-flammable. And also the dendrite growth in lithium batteries is a huge problem. And this is not the case in aluminium batteries.
Okay, thank you.
Thanks.
Tim?
It sounds like you've made some really big steps in your research, so congratulations for those. You indicated that your polymers are now stable for more than 1,000 charge and discharge cycles. What would be ideal for you? What are you aiming for in terms of the number of charge and discharge cycles? Is 1,000 enough, or are you going to aim for more?
For batteries, in fundamental research, we start to talk when the battery reaches at least 500 charge and discharge cycles without any major degradation. Then we start to talk about feasible systems. So 1,000 is quite good.
How easy is it to recycle the non-aluminium elements of your battery?
The non-aluminium elements would be the conductive polymer. They can be easily decomposed. So I'm not putting my focus on the life cycle analysis, but the polymers can be easily decomposed regarding our colleagues who were dealing with this. And the ionic liquids are also non-toxic and can be simply dissoluted or also recycled and to a new electrolyte.
Okay, great. Thank you very much. Okay. So next talk is Jessica Taylor from Cranfield University, who's studying at the National Structural Integrity Research Centre. Jessica, over to you. 3 minutes.
Hi, I've just finished my first year at Cranfield University looking at crack arrest. So typically when we design a structure, for example, a ship or a wind turbine support structure, we design it to avoid crack initiation. We do this by designing out complex welds or crack concentration points. So the crack initiation methodology is an alternative to this approach. It's a kind of fail-safe approach by which a crack is arrested in the bulk material, having initiated at a localized stress concentration or weak point, usually in the weld. We do this by designing the material, perhaps through grain refinement or through hot rolling of the plates. And this has applications in the pipeline industry to protect against accidental damage of an anchor dropping on a pipeline, which will release oil, or in the shipping industry to protect against accidental collisions. So what I'm looking at is the way that we can improve this methodology. So at the moment, the methodology is outdated. We rely on empirical equations which were formulated for steels that were in use in the 1960s and 1970s. And these are simply not the steels that are in use today. We don't know if the current methodology is going to be valid for these steels. This is particularly important because there's been a recent drive to build larger container ships which can carry more load, and this will reduce their environmental impact. There's been a drive to build larger wind turbine support structures, which can carry a larger turbine, which will produce more energy. These require thicker sections of steel, which have got a higher strength, and this requires also more complex welding procedures. All of these increase the chance of a crack initiating in the structure. So what we would really like to do is to be able to bring a methodology to use the small-scale properties of the material through small-scale tests that can be carried out in the steel fabricators to determine the large-scale properties of how the material is going to act in service, to try and ensure that we can arrest a crack once it's started growing before it reaches catastrophic failure and the lives are at risk of people on board a vessel or oil is spilled out of a pipeline, which is going to damage the environment. So, thank you very much.
Okay, questions, please. I'll kick off. What sort of mechanism are you looking at? Are you looking at doing something to the material? Are you looking for a mechanical solution?
For the moment, I'm just looking at the material properties. So we're not sure exactly what is the mechanism behind a crack stopping growing. We're fairly sure that we know why a crack will start growing. And it's always been assumed that a smaller grain size, grain refinement, will stop a crack from growing. However, there's some materials that have been being used recently in the pipeline industry which have got a very high toughness to crack initiation, but once the crack has started growing, it will just continue growing all the way through, which they're very adamant to protect against in the pipeline industry. Since there are a lot of anchors get dropped on pipelines, there's often cracks will start to form. So we're not sure exactly what it is that the mechanism is, but we're looking at trying to create look at finding more relationships between different material properties.
Okay, thank you. Anyone else? Richard? Oh, no, one over there first.
In terms of the mechanism by which the crack is stopped, have you looked into functionally graded materials, just as a possibility? I know 3D printing is something the scale of like a pipe or a ship isn't really feasible at all, but perhaps cladding, so you can have like a more ductile layer to arrest a crack that's progressing through a brittle material.
One of the things that's done is often thermomechanical heat treatment. So the plates are rolled to make sure that the outer surface is sort of more resistant to the crack growth, and then it's sort of slowed through the shear lips forming on the outer surfaces. But obviously, as you said, additive manufacturing is going to be much too costly for ships or for wind turbine support structures. But they are looking at perhaps alternative methods for the jacket structures for the wind turbines that have a lot of different welded nodes, perhaps casting the nodes to try and reduce that welded element so that you can sort of avoid that concentration there.
And Richard.
Hi. Cracks seem to get a bad press. Are there any materials or situations where cracking is a good thing?
I don't know about that. I haven't come across any situations where cracking is a good thing. Typically because once you've got a crack, it will either continue going through fatigue, or you've got if it's a brittle crack, then the entire structure will fail. So I'm not sure about that. I think it's probably unlikely.
Okay, thank you very much. Well done. So we have one final talk. Heather Turnbull from the University of Aberdeen. Heather, 3 minutes. Over to you.
Wind energy generated over 11% of the EU's electricity demand in 2017. With 2018, some of the world's most powerful wind turbines installed in our very own Aberdeen Bay. The wind energy industry has undoubtedly demonstrated rapid growth in recent years. However, remote operational environments, manufacturing processes, and extreme events, among others, can pose challenges. Damage to wind turbine blades in particular can be catastrophic, with implications in terms of asset integrity, production and economic losses, and most importantly, safety of personnel. Now if we take a step back for a moment, you wake up one morning ill. Do you wait till your 6-monthly routine doctor's appointment and hope you don't get any worse in the meantime, or do you make an appointment with the doctor? Current visual inspections for wind turbine blades are largely visual inspections at predefined intervals. As with our analogy, these are usually insufficient as they can be subjective, and damage occurring between scheduled intervals can propagate into serious secondary damages. To this end, we propose vibration-based structural health monitoring methods, in which we utilise a network of sensors permanently attached to the blade, and the premise that structural change will manifest itself through a variation in the dynamic behaviour of the blade. In our research, we've adopted model calibration for detection, localisation and severity assessment of damage. Through construction and minimisation of an objective function containing analytical and experimental model parameters, we're able to obtain numerical models which better reflect the reality of the system. During model calibration, uncertainties can affect the accuracy of the solution, which has led to the development of uncertainty quantification techniques. Motivated by this limitation, we have developed a non-probabilistic technique known as based on fuzzy theory, which allows us to quantify uncertainty in a meaningful way. On a wind turbine blade, we simulated 5 damage scenarios and experimentally, and used numerical models to try and predict the magnitude and uncertainty associated with these parameters. As a result, we managed to obtain an accurate prediction for each of the 5 damage scenarios and quantify the uncertainty associated with each of the parameters. And we think this is going to have an industrial impact, including remote monitoring after extreme events and minimisation of unnecessary inspections. Thank you for listening.
Well done. And questions, please.
Well, we're currently running on the Maxwell supercomputer in the university. So for minimisation of objective functions, it's quite a lengthy process, the optimisation. So we're currently running in parallel on our supercomputer. So, yeah, yes, we got it there.
Another one back here.
Which kind of structural response do you use? Vibrations or... And what kind of sensors do you use? PCTs, accelerometers?
So it's vibration-based structural health monitoring we're working on. So at the moment we're collecting the natural frequencies of the blade. And in relation to your question on the sensor, we're using piezoelectric sensors on the blade in the laboratory.
Hi, Johan Gunnarsson from Lloyd Foundation. What you've been mentioning is what you have been doing as a group, and research is really collaborative, but I would like to, if you could just spend a few seconds on your own contribution. So instead of saying we have, I have, what would that be?
The term we and I interchangeably, to be honest. So it's pretty much, I'm pretty much working with my supervisor, Dr. Muntasir, but I'm pretty much working alone on this project and obviously supervised by my supervisor. So it's very much, I have done this.
Okay, and we go, yep.
Alexey from the Institute for Risk and Uncertainty. What is the advantage or the justification for using a non-probabilistic method over using probabilistic modeling?
Yep, so this is something I get asked quite a lot, but I'll try and keep it short. Basically, it's the way you actually define your updating parameters, essentially. In a probabilistic method, you would make an assumption regarding the probability density functions of your updating parameters, whereas in our method, we make no assumptions regarding the unknown variables. We model the uncertainty in the response parameters, and then propagate that back through the model. So that's the main difference there, I suppose.
One final one from Tim.
I was just wondering if attaching the sensors, however you do that, does that have any impact on the structural integrity of the blade?
Well, so currently we're working with a 7.2 kilogram blade, and our mass of our sensors are actually around about 3.5 grams. So at this point, no. We don't think it has much of an impact on, obviously, the mass, but obviously that is a concern if you were attaching more, a lot or heavier sensors.
Great. Thank you very much. Well, thanks. Well, what a wonderful session. I didn't have to use my prop once, so I think we'll give them a round of applause. Yeah. And the judges will confer over coffee. The winner will be announced later this evening. So we now have a coffee break, 20-minute break. Please make sure that you are back here in good time for starting off at past. Since I do have a comedy prop, those of you from outside the UK, we have new pound coins. Do people like the new pound coins? No, I don't either, but then I've never liked change.